Now let's get into the details of three-phase transformers. As you know that power transmission through three-phase circuits has numerous advantages when compared with other polyphase systems. So for three-phase power transmission, here we are making use of three-phase transformers. Let us consider a simple power system where here this is the power generating station and the power generated is being stepped up with the help of three-phase step-up transformer, and then it is transmitted through transmission lines, and then the transmitted power is stepped down by step-down transformer and then distributed through distribution lines and finally to the load. Means the power generated is being transmitted and distributed to the load with the help of three-phase transformers. Here this transformer is step-up transformer which is used for stepping up the voltage level, and here this transformer is step-down transformer which is used for step downing the voltage to a desired level. As per definition, transformer is a static device which is used to transfer power from one circuit to another circuit without change in frequency, and which is accompanied with increase or decrease in the voltage levels. And this three-phase power transmission can be done in two ways, that is either by using three single phase transformers or by using a single three-phase transformer. That is, here power can be transmitted by using either a single three-phase transformer or we can transmit the power by using three single-phase transformers. So here are the important differences between three-phase transformer and bank of single-phase transformers. As it is discussed that power transmission is preferred through three-phase circuits, and that transmission can be through a single unit of three-phase transformer or a bank of three single-phase transformers. So from this you can observe that here all the phases are magnetically isolated. That is, observe that here each phase will have different magnetic circuits. Means here all the three phases are magnetically isolated. And coming to this three-phase transformer, here as all the three phases are wound on single magnetic circuit, so here no magnetic isolation. And now coming to the case of floor area, as this is single unit, it occupies less floor area, whereas here occupies more floor area. And in case of fault, in any one of the phase, so if there is any fault in one of the phase, the entire unit must be disconnected. Means now there is discontinuity of supply. Then power interruption takes place. That is, power interruption occurs. And coming to this case, if there is fault in any one of the phase, that can be disconnected and the continuous supply can be maintained with the other two transformers, and how it is will be discussed later. Okay, now let's continue with this point. So continuity of supply with other two transformers in case of fault in one of the transformer. And now coming to the case of application. So in case of hill stations, it is easier to carry single phase transformers when compared with carrying a bigger unit of 3-phase transformer. So used in hill stations and also where transport facility is not good. So when the transport facility is not good, in that case bank of single phase transformers are preferred, and in this case used where transport facility is good enough. These are the important differences between a 3-phase transformer and bank of single phase transformers. And now coming to magnetic core construction. So the types of 3-phase magnetic core constructions are 3-limbed core type construction and 5-limbed shell type construction. Okay. In single phase transformer, we have seen that if this is the magnetic core for which the primary winding and secondary winding are wound, let us suppose this is the primary winding and this is the secondary winding, and this type of magnetic core construction is called core type construction, in which winding surrounds the core. Whereas in case of single phase shell type transformer, if this is the magnetic core, then the winding will be like this. This is primary winding and let this be the secondary winding. So in case of shell type transformer, core surrounds the winding, and it is discussed that to decrease the leakage flux, half of the primary winding is wound on one side of the limb and remaining half of the primary winding is wound on other side of the limb, and similarly half of the secondary winding is wound on one limb and remaining half of secondary winding is wound on other limb, which means on single limb we can have half of the primary winding and secondary winding. That is, on single limb we will have both primary winding and secondary winding. And now come to the case of 3-phase transformer. Primary side winding let us represent with R1, Y1 and B1, and secondary side winding let us represent with R2, Y2 and B2. So according to our discussion, the 3-phase transformers consists of 3 cores. One core for this winding and one core for this winding and one core for this winding. So let us suppose this is core for R winding, and let us suppose this is the core for Y winding, and let us suppose this is the core for B winding, and it is discussed that both primary winding and secondary winding present on same limb. So if this is R1, so then R2 also will be on the same limb, and similarly if this is Y1, that is primary winding, and this is Y2, secondary winding, and similarly if this is B1, primary winding, and let us suppose this is B2, secondary winding. Let us suppose flux phi r is the flux due to R1 winding, and let us suppose this is the flux phi y due to Y1 winding, and let us suppose this is the flux phi b due to B1 winding. So if you observe that flux phi r, phi y and phi b will meet at this junction, means here phi 1 plus phi 2 plus phi 3 will be 0, that is phi r plus phi y plus phi b is equal to 0, which means at center of the limb there is no flux. And if there is no flux, what is the use of placing this portion of core? Which means to save the core material, this portion is removed. That is, there is no usage of placing core material here. So now this portion is removed. Now there is no center limb, and if you take the front view, this core will look like this. Means it will look like a three-limbed core, which is our discussion, that is three-limbed core type construction. Our one limb R phase winding is wound, and our other limb Y winding is wound, and over the third limb other winding is wound, that is B winding. And this type of magnetic core construction is called core type construction, because here winding surrounds the core. And now coming to shell type construction. Okay, this is single phase transformer shell type construction, and coming to three phase shell type construction, it will look like this, which is also called 5-limbed shell type construction. So this construction consists of 5 limbs, 1, 2, 3, 4 and 5, and R winding is placed over here, and Y winding is placed over here, and B winding is placed over here. Means here, if you observe that the core surrounds the winding, which is called shell type construction. Means this is the 5-limbed shell type construction. And coming to applications, usually core type construction is used for high voltage and low current applications, whereas shell type construction is used for low voltage and high current applications. Here my focus is not to tell you what is core type construction and what is shell type construction, and the important thing that we must learn from this is now I am going to tell you. In the introduction on three-phase transformers, I mentioned about harmonics, in which I asked you to focus on triplent harmonics, because triplent harmonics are the harmonics because of which we are getting non-sinusoidal output, and those triplent harmonics are present in the phases along with the fundamental signal, and they doesn't present in lines, and they present only in the phases. Because of those harmonics we are getting non-sinusoidal output. So to get pure sinusoidal output, we must reduce or eliminate them completely to get pure sinusoidal output. And coming to three-limbed core type construction, so these are the phases, and along with our fundamental signal we will have triplent harmonics. And similarly, this is Y phase and this is P phase. So let us suppose from R phase, phi R is the triplent harmonic flux, and similarly from Y phase, phi Y be the triplent harmonic flux, and let us suppose phi B be the triplent harmonic flux. And it is known that triplent harmonics are having zero phase sequence, means they have 0 degrees phase displacement between each other. Means all the 3 harmonic fluxes start at same time and reach this point same time. Means one flux doesn't have the path to flow through this way, and similarly this flux will not have path to complete, and similarly this flux will not have path to complete. So they remain in the phases, as these triplent harmonic fluxes doesn't have path to flow through the core, they take the path through the air. Means they get neutralized by taking path through the air. So in case of three-limbed core type construction, irrespective of the type of winding, that is whether it is star or delta connected, we get pure sinusoidal output from three-limbed core type construction. This is the concept what I am trying to tell you, and this concept you can understand only if you know triplent harmonics. So I suggest you to go through my lecture videos on harmonics, which I mentioned in alternator lectures. And now coming to shell type, observe that This is the one phase, R phase, Y phase and B phase winding, and it is discussed that in phases there will be triplet harmonics, and one triplet harmonic can take this path. Similarly, other triplet harmonic fluxes will have other paths. So here the output is sinusoidal or not depends on the type of winding we employ here. Okay, here triplet harmonics took the path of air and got neutralized. So output is sinusoidal irrespective of the winding, whether star or delta. Whereas in this case, triplet harmonics are taking the path through the core. So here the output from the phases is either sinusoidal or not, depends on the type of connection, that is whether star or delta employed. And along with this, I suggest you to go through the video on the type of input that must be given to the transformer to get sinusoidal output. Please go through that video. From that you will know that to get sinusoidal output for transformer we need to give peaky waveform. Okay, if you give pure sinusoidal input we will get non-sinusoidal output, and how it is means you must go through that video to understand. And now let's get into the important topic from three-phase transformers, that is winding connections. In simple power system, the power generated in power station is stepped up to higher voltage levels by step-up transformer and then transmitted to transmission lines, and then it is stepped down to desired voltage level by step-down transformer and then distributed through distribution lines and finally to the load. Means here the power generated is being transmitted and distributed to the load with the help of three-phase transformers. So this is the importance of transformers in simple power system. And now here we need to discuss about the winding in case of three-phase transformer. In three-phase transformer, which consists of primary winding and secondary winding. In three-phase transformer, all the three primary windings are connected in delta or in star, that is here we are considering RYB phase sequence, means R phase, Y phase and B phase. So on primary side, R phase, Y phase and B phase winding are connected either in delta or in star. And coming to secondary side, all the three secondary windings are connected either in delta or star. And also there is special connection, that is zigzag connection, and depending on the type of connection employed in three-phase transformer, the power transmission depends. So there are four important connections in three-phase transformer, that is delta connection, second star connection, and third star delta connection, and fourth delta star connection. Star connection can also be called as Y connection. And there are special winding connections, that is star zigzag star connection and delta zigzag star connection. And along with these connections we are going with special connections like open delta and Scott connection. And from each of these 6 connections we are going to see the winding connection, that is how to connect the winding, and then the phasor diagram, and then identifying the vector group, and then phase voltage ratio and line voltage ratio. So these are the things that we are going to discuss from each connection. Here you must note that we must know what is vector group. So before going with these winding connections, there is necessity to discuss what is vector group. Vector group. Vector group is a symbol used to identify the winding connection of HV winding and LV winding, and along with that it will give the information of secondary voltage phase shift. That is, it will give the information of secondary phase to neutral voltage phase displacement with respect to primary phase to neutral voltage. Let us suppose this is the vector group mentioned on nameplate detail of transformer. So by observing this, we can say that first character, which represents HV side, means HV winding is connected in star, and second character represents LV side, means here LV winding is connected in delta. Secondary phase to neutral voltage phase displacement with respect to primary phase to neutral voltage, and that is based on clock notation. That is, we know that if this is the clock and the numericals on clock is like this, and the angle between two consecutive numbers is always 30 degrees, and now here 5 means from clock notation it is 5 o'clock, and here this numerical will indicate the phase shift, means the angle between minute needle and hours needle. So here the angle between minutes needle and hours needle is 1, 2, 3, 4, 5. So 5 into 30, 150 degrees, means here the secondary phase to neutral voltage displacement is 150 degrees with respect to primary phase to neutral voltage. And according to BIS, Bureau of Indian Standards, there are certain rules to be followed for vector group. So here the first character is in caps, means is represented in capital letters and indicates HV winding connection. So first character must be represented in capital letter, and that will indicate the HV winding connection, whether star or delta. And second, that is second character, is in smaller case. That is, the second character must be always represented in smaller case and indicates LV winding connection. So irrespective of what is primary and secondary, always in vector group, first character represents HV winding and second character represents LV winding, okay, and third numerical indicates secondary phase to neutral voltage phase displacement. Based on clock notation. That is, if suppose this is the clock and the angle between two consecutive numbers in a clock is 30 degrees, and HV side phase to neutral voltage is taken as reference and represented with minutes handle. So HV side phase to neutral voltage is taken as reference and that is represented with minutes handle. So minutes handle always points at 12. So minutes handle always is placed pointing towards 12 because HV side phase to neutral voltage is represented with minutes handle and it is taken as reference. So minutes handle will be always at 12 and LV side phase to neutral voltage is represented by hours handle, which means here as we took the example like this, so hours handle must be pointed towards 5 and this represents the LV side phase to neutral voltage, and from this example 5 will indicate the secondary voltage phase displacement. Means here from clock notation the angle between minutes needle and hours needle will give you the secondary voltage phase displacement with respect to primary voltage. So here the angle between 12 and 5 is 150 degrees. Means the secondary phase to neutral voltage has a phase displacement of 150 degrees with respect to primary phase to neutral voltage. This is about vector groups.